Welcome everyone for the third part of the tool training on the performance-based engineering application and related tool that we call Pelican. Thank you for joining us today. And we have quite a few things to talk about, so I will start and jump right into it. I have this recap slide here. We saw that yesterday, we saw that on the first day. I don't want to spend any time on this. I just included it so that when you download the presentation slides, if this is the first day that you joined us, you will see some important information on how to set up and prepare your environment to run the examples that I'm going to show you today. Yesterday, we had no example files because we used the examples from the first day, but today we do have new example files. So I encourage you to go to DesignSafe and download them as well as the slides that I'm showing right now. And I would like to remind you that we have this message board and we are eager to hear your feedback about the tool training and the tool in general. Your feedback really drives our tool development. We would like to know if you find these tools useful and if you find these tool trainings useful. This is how we decide how many of them we hold over the year. So if you think you would like to hear more about these tools, please let us know. We are happy to have more webinars. Okay, so you see the outline for the 3-day trainings. We have done the introduction to the PBE application. Yesterday, we talked about advanced modeling options in the PBE application. And today, we are going to look behind the application, behind the user interface, and see how it works and how Pelican, the engine behind the PBE application, works and how you can run it without using the user interface. Yeah, there are 5 steps that we are going to go through today. We will start with the workflow, then look into the output data that is generated. I will talk a little bit about Pelican, what it is and what we are developing there, and then show you explicitly how to run loss assessment with Pelican. And I will finish the presentation with a roadmap for PBE and Pelican, where I will show you what you can expect in the future. But as I mentioned, you can influence these developments and you can kind of not decide, but let us know what you are interested in, and we will take that into consideration. So let's start with the workflow, and then I will put this presentation out of presenter view and walk you through step by step this workflow and show you how the files are generated and where they are stored, so that if there is an issue with the workflow, you will be able to see where it might have happened. You will be able to let us know or give us a better description of what failed, and perhaps even figure out yourself what the problem is, which makes it easier to work with the tool. It also allows you to extract certain intermediate data if you are interested in that, or maybe that helps your research to know that intermediate data. So, you know, at a very high level, what happens is that we have a front end, which is the user interface and related high level script. And then that front end runs the back end, which we always display as like these puzzle pieces, which emphasizes the modularity of the backend. But essentially what it's doing is it's running through a workflow that is, for EEUQ, it's a little shorter, for PBE, it's a bit longer, and then for the RDT tool, it will have the full setup of applications, a full system of applications. Once this workflow has run, we pass the results back to the front end and display them for you. So that's at a high level. Now let us go to a little lower level and see what is happening. So when you click the Run button in the application, and we will actually do that right now. So we will go to this application, open a file. This is from today's examples. We will go the first day. We will start with a simple example. We'll start with this HAZUS assessment. If you remember, that was something we ran on the first day, but I will switch the event file or the event application to the stochastic one, because I don't want to run into any trouble with the USGS web service. So I will just run this very simple stochastic ground motion generation and keep everything else the same. So this is the HAZUS input file from the first day, and run it. And resume presentation as well. Okay, so in this directory, now you see all the results, but we will go through again step by step. So first, when you click the run button, the PBE application creates a Dakota JSON file. This JSON file is a configuration file for the whole analysis or simulation. And it contains detailed information about all the settings that you have in the PBE app. This is the same for the other applications, but the amount of data is a little bit less because they don't have loss assessment in there. If you are interested in how this actually looks like, I can show you an example. So this is the Dakota JSON file. If we open it, you can see that it's human readable. We have the list of applications that are requested in the workflow. So for each step of the workflow, these are the puzzle pieces, if you wish. We have a different application identified. And then for each of these, we have detailed information about the settings that were set in the PBE application. So this is damage and loss, and we have events, general information, simulation, structural information, UQ, and so on. So if you are interested, you can read this file yourself, or you can even change details that are set here. And actually, you can load this file back into the PBE application. So if you wish to modify the settings, you can modify them here in the file and simply click File, Open, and load the file back, and it should work fine. Now, once this Dakota file is generated, we move on and start the workflow script. The workflow script is a Python script that connects the different applications in the workflow and makes sure that the data is passed between them. This Python script, if you are interested, is located in the applications folder in your PBE directory. So now this is your PBE directory. I put it in the NHERI SimCenter folder. This is what you downloaded from DesignSafe when you got the application. You start PBE with this executable, and within the same folder, you have an applications directory. And you see that here are the puzzle pieces that we have. So EDP, event, SAM, damage and loss, simulation, uncertainty, quantification. We also have a workflow folder, and this contains the workflow scripts. In this case, this is the PBE workflow.py, and this is the script that controls the simulation and controls the workflow. Again, if you are interested, you can open it. It's very easy to read it, especially if you know some Python. You can see that there are comments, and it's not a really long script. So you can see what is happening, and by following these links and by following these functions, you can get more information about how each step is run. It takes use of this whale package, which is right there in the same folder. So if you are interested, if you want to dig deeper, you can do it that way. Now, this script does a couple of steps, and I will lay that out here. First, it initializes the random variables. You remember that we have uncertainty quantification all around our application. While you are going through these steps in the user interface, you can assign random variables to various parameters. Those random variables are prepared and initialized in the files as a first step. And when you look at the template directory here, these files are created as the first step, and these files contain already those random variables. And also there's a workflow driver here that is a bash script to run the workflow, to run the specific applications that were identified in the user interface. If you open this file, you will see that those are simple commands that call the various application files and scripts here in the application folder. So one of the applications in each of these modules are called by that workflow driver. Now, once this is done, we go to the next step and run Dakota. Dakota handles our uncertainty quantification and propagation, and it uses this workflow driver and creates a different working directory for each sample that it runs. So now we are running 20 samples in this example case. So we have 20 workdirs, and in each workdir, we have the original files from the template dir, and then we use the applications that are defined in the workflow driver to take these files, pass them along the workflow, and create the results, process the results, and finally pass them back to Dakota. Dakota collects the results in the Dakota tab.out file, and we take that and create a response.csv that is probably easier to read in MATLAB or Excel or any other script that you use. If you open this file, we have seen that yesterday. This is a file that contains all the random variables that you had with samples and all the response EDPs that came out of the analysis. So this is still only up until the response estimation step. And then we take that response CSV and pass it to the DL calculation Py, which is our Python script for running the damage and loss assessment. This file is located in the applications folder. So under your PBE directory, in perform DL, Pelican right here. So this script is called using the response that we got from the response simulation, and also using the Dakota JSON, because that's where we have all the details of the damage and loss assessment laid out. This script calls Pelican, which I'm going to explain in a little later, and then performs the damage and loss assessment and produces a number of files that we have right here. You see all of these CSV files are created by the damage and loss assessment. Some of them are used to show the results. Actually, the first two are used, only the summary. The summary results are loaded by PBE and then displayed in the user interface. These are the data that you see here. So, for example, this repair cost data, just like that. This came from that summary CSV file. So this is the workflow. This is how it looks like when you request response simulation as well as loss assessment. If you provide your own response data, then the workflow is a bit different because we don't need to run through the response estimation. So it's going to be a bit simpler. I will come back there. It's going to be a bit simpler because we have the response data here, and that response is directly passed to the DL calculation script. We perform the loss assessment and pass the data back to PBE. Now, what I also wanted to mention is that we have these log files created, 3 of them by the 3 different parts of this calculation process. We have a debug log that records what happened in the front end. We have a log file that records what happened in the back end. And we have a separate log file that goes into the details of the loss assessment. So if you run into some errors, we would like you to locate those log files and send them to us, because these provide information about the details and perhaps what went wrong. You might also find these log files useful. Let me show you how they look like. The debug log is a bit difficult to comprehend, so I wouldn't start there. But if you look at the log file, which is for the workflow scripts, so for the backend, it's actually quite easy to read. You can see what applications are available, and you can see how they were run. And if there's any error, you will be able to see that this is a workflow that ran properly. If there's an error, you will see an error message here that is probably readable, and you might recognize what went wrong. If you don't want to get into that,
just send us the log file and we will be able to interpret it. The Pelican log is only about the loss assessment, and it provides you detailed information about what components were used, how they were interpreted, and if there's anything wrong or warnings, it will also show that. Okay, so this is how our workflow runs. It's how it works. Now let me continue and show you what kind of output data it produces. For this, I prepared a Jupyter notebook that is also part of your example package. So if you can work with Jupyter notebooks, you can use this for any of the analysis that you do in the future to quickly look at the files. But of course, these files can be loaded into Excel or MATLAB or any other tool if that's what you fancy. So here you see that there's a Pelican outputs IPy notebook. You can use this to visualize the results. I have this prepared here. Pay attention at the beginning. You need to set the directory where we load the results from according to what's where it is located in your system. It's pretty surely not in this folder because this is my username. So you will need to replace that with your name. Other than that, it should work just fine. I will run a more detailed analysis. This is today's example, just to have more realistic results that are something that you would have from a loss assessment that you do in the future. So I prepared a 6-story buckling restraint braced frame analysis. We are going to provide the responses. Those are also included in the zip file. And this performance model has much more components that are predefined with reasonable quantities. So we have something that is, again, more realistic in terms of loss assessment results. And I'm taking advantage of the truncated distribution and so on. So if you look into the details here, you will see that this is a bit more complex than the basic examples from the first day. Since we are providing these responses as inputs, we can expect that this will run pretty fast. So we will see the results soon, and we will be able to load those results into the Jupyter notebook. Now, while it is running, let me show you a quick overview of what results are available. So there are 4 groups that I'm going to go through. We have EDPs, we have damage results, decision variables, and then summary results for the whole loss assessment. That's like an overview. That's what we load into the PBE application. So starting with the EDP results, while the calculation is ongoing, there are 2 types of files, as I'm going to show you. And this naming convention applies to all of the other result types or outputs. The base name is always a file that includes all the samples for every realization. So in the case of the EDPs, this includes the collapsed cases as well. And then different suffixes are used to identify post-processed files that makes it hopefully easier for you to get some information without the need to process these samples. So in this case, for example, for the EDPs, we have the EDP stats that provides statistics for each EDP. And I will show you an example right now. I see that the calculation completed, so we can go to the Jupyter notebook and start loading the files. So we just start running these cells. I'm running them as we speak. This should be quite fast. So first, we are going to load the EDP CSV file. So this file that includes all the samples for every realization. And this is what we get. You can see that we have 10,000 rows in the file. So that means we have 10,000 samples and 26 columns. That stands for the 26 different EDPs. You can see that the header identifies the type of EDPs, and this is not the input. This is the resampled EDPs generated within the loss assessment. So we provided 30 EDP samples and then got back 10,000 because that's what we asked for in the PBE application. You see that these are peak floor acceleration values. And then as we scroll, we reach the peak interstory drift values in direction 1, and then in direction 2. We have 6 stories, so altogether we have 24 plus 2 columns, I believe. All right, so one thing that I wanted to point out related to yesterday's presentation about the different distributions, we asked for a truncated EDP distribution, considering only non-collapsed cases, and this is exactly what we got. If I plot it, you can see that we set the collapse limit at 8% drift, and indeed we get a log normal distribution that is truncated at 8%. So none of the EDPs exceed 8%. That's how you can take advantage of this truncation feature. Another thing that is interesting that this applies to multiple dimensions. So now I'm going to plot the first floor drift ratio in 2 directions, direction 1 and direction 2. This is a plot I created earlier just to make sure this works, but I recreated it now using the live data that I just got. And you see that in both dimensions, the drifts are limited to 8%. So if I change this to a peak floor acceleration, just to show you that this limit only applies to the drifts, you can see that the accelerations have no limit while the drifts are limited to 8%. I cannot show you all the different joint distributions because that's just too many dimensions, but you can play with this file and you can plot any 2 combinations here very easily. So that's how these work. Now let's see what happens with the damage measures. So the damage is, oh, sorry, I wanted to point out this one as well. So we have statistics. You can see that in this file, we have the same header and we have those mean, standard deviations and various percentiles that I mentioned for each of the EDPs. So this makes it easy to have a quick look at what outputs you have and how they are distributed. And now go on to the damage measures. So for the damages, we are looking at first the basic file, the dmg.csv file. And that file is pretty big. It has a lot of details in it. We have a header with 3 rows. The first one identifies the fragility group. If I scroll in, you see that there are other fragility groups. Okay. These fragility groups are labeled according to the column, component ID that you set in the performance model. So this B1031001, if we bring up the PBE tool, go back to the components, we can see it's exactly this ID. So those results below it belong to the, or correspond to the voltage shear tab gravity connections. The second row identifies the performance group. Each fragility group has a couple of performance groups corresponding to it. And then these labels are structured as follows. You can see it here in the presentation. First, we start with an ID for the fragility group. That's just a number starting with 1 and increasing with each fragility group. So this one starts at, this is 1. If you go to the second group, it's 2, and so on. So it starts with 1. Then we have 3 digits that identify the location. This allows you to have as many as 999 locations in the performance model. So this 1 means it's the first floor, this is the second floor, and so on. And then the last digit identifies the direction. So again, direction X and Y in this case, and again, X and Y. So this part until this point is this component on the first floor in the first direction. And then we have the 4 damage state groups or damage states. This is a concept introduced in Pelican, but it's very similar to what's already in FEMA P58. A damage state group is a group of damage states controlled by the same fragility description. And then a damage state within there is separating different consequences and different types of damages. So for example, in this B1031 case, we have the first damage state group, which means this group these two damage states are controlled by the same fragility function, but within that group, we have these two damage states instead of just one, because there are two possible outcomes of that damage. That's usually referred to as simultaneous or mutually exclusive damage states within a group in FEMA P58. In this case, these are mutually exclusive damage states for bolted shear tab gravity connections. So it's either this one happening or the other one happening. And this file shows you which one happened with how many, how much of the component quantities. So if we go back to the PBE application, we can see that for this component, we identified that in each performance group, we have a total of 20 components. We have the unit as each. So that means we have 20 bolted shear tab gravity connections, and they are grouped by 4. So that means four connections will have the same damage out of the 20. So they can get damaged in groups of 4. That's why we see multiples of 4 here in the damages. So for example, in realization number 3, we have 16 connections in damage state 1-1, and we have 4 in damage state 2-1 on the first floor in the first direction. And then for each realization up to 10,000, you can see that we have a different number of damaged connections at the various places in the building. And if you scroll on, you can see other components and their damages. Sometimes their unit is not each. So for example, if we go to the facade, we see that the units are, I think that's feet. We can check it here. Yeah, it's linear feet. So we have 60 linear feet altogether grouped in 2. And notice that we put some uncertainty on the amounts. And that's why we are not seeing 30 here, but 33 or 32 or 27, depending on what the quantity sample is for that particular realization at that particular floor and direction. So this is, again, just to remind you, this is fragility group 5 on floor 1 in direction 1. And the various damage states, this particular component has 2 damage states, the first one and the second one, and that's it. And then we go to the next floor or the next performance group and so on. Right, so that's how it works. And this is a lot of data. Oftentimes you don't need this level of detail. So we provide a couple of other files. The DMG stats file gives you statistics. So essentially it aggregates across these rows. Instead of providing these 5,000 non-collapsed information, you get only this many rows, and it provides the same kind of statistics that we have already shown for the EDP data. The AGG file is an aggregate file where we aggregate across columns. So you can see that we start with the fragility group and everything below is aggregated. So these 2 other layers, and I give you the damaged quantities of each component of each fragility group. So it's a much shorter list. It's still, quite some columns because we have quite a few fragility groups introduced in this model. This can be useful if you want to have a quick overview of which component got damaged and how many of them. Now, for the decision variables, it's going to be a very similar system. We have 4 types, typically reconstruction cost, reconstruction time, injuries at different levels, severity, and red tag. The basic file provides the same kind of information as the same kind of structure as the damage file. So here you can see that we have the fragility group, the performance group, and the various damage states, and then the decision variables that correspond to the damages that are experienced by that component at that performance group. So in this case, we are looking at reconstruction costs. So this is in dollars. You can uncomment a certain line to look at different types of decision variables within this file. If I move to the presentation slide here, you can see that these are the files available. So basically we are reading a different file when you choose a different decision variable type here. Again, we provide aggregates. So aggregate these decision variables across performance groups and damage states here. So you can see which component is driving that particular type of loss. Again, in the case of reconstruction cost, these values are in dollars. And you can see, for example, that while these components lead to a couple $100,000s of damage, these components introduce millions of dollars. So you can see that these are probably more important when it comes to the losses. And that's just an example. So you can disaggregate the losses using these files. And then if you don't want to look at all of the rows here, you only want to see some statistics, you can use the AGG stats file, which gives you the same kind of statistics that I've shown you before, mean, standard deviation, and then some percentiles of the losses for each fragility group. And finally, we have a summary file and its statistics. The summary file provides you the kind of data that is displayed here in the PBE application. So this is the data that is read by the application and is used to display these plots. You can see that we have the columns, the same columns that are in the PBE app. And in the first case, we have 10,000 rows. An important difference between the summary and these raw data before is that this file includes the collapsed cases. So if you would like to know which IDs correspond to the collapsed cases, you can use this file and look at the collapsed column. 1 means it's collapsed and 0 means it did not collapse. The statistics file is the highest level of information that you can get. It has only a few columns and this type of information. This is what we use in the PBE application to give you a summary, an overview of what happened. So these are the different output files that are available. I hope this helps you to understand and start using them. If you are interested in other types of information that is not included in this file, please let us know. We can extract any other information from the analysis, and I'm happy to add new files and provide you even more information if you find that helpful. And now I will jump to another part of the presentation and talk a little bit about Pelican and what it is and what we would like it to become. I would like you, if you are interested, to take a look at the GitHub page of Pelican, where you can look at the source code. You can even check out the source code and change it, edit it, and use it as you please. We have a very permissive license, so I think you can really take advantage of these developments. And if you are interested in the framework that is implemented, then I encourage you to check this preprint of a paper that we wrote for the World Conference, and that will provide you more technical details and more theoretical information about how this framework works. In short, Pelican stands for this probabilistic estimation of losses, injuries, and community resilience under natural disasters. It's not just a software, but it's also a framework of different methods and tools. And we strive to, you can think about it, that we strive to create something like OpenSeas, but not for response estimation, but for damage and loss assessment. So we would like to have a community-driven development of various methods and tools that you can combine into various types of analysis for damage and loss assessment. So you can think about it like this. Pelican right now is a library. So it's a set of different tools, fragility functions, fragility models, correlation models, and so on. And you can use that to assemble a script or an application that does assess damage and losses and its consequences This application is our DL calculation script that runs the loss assessment behind PBE. And then that application becomes part of a bigger picture, a puzzle piece, if you wish, in our workflow. And that's how we run the application, run the PBE app. If you would like to use Pelican for something else, it's very easy to just take these functions, assemble a different application, and use it for a different purpose. That's the idea. To give you a quick overview of where this Pelican is evolving, I would like to show you the history and how we got where we are. We started in 2018. Pelican is based on the FEMA P58 method, but it does not only implement the method, it tries to go beyond it and tries to become more generic than that method. So we started with that high fidelity loss estimation method and the PBE app back in 2018, but then we expanded by adding HAZUS, and adding means expanding the method to incorporate both FEMA P58 style assessments and HAZUS style assessments within the same framework. And we have a test bed where we demonstrate how this works for the San Francisco Bay Area under an earthquake hazard. Then we expanded to hurricanes. So it's not only limited to earthquakes, but now we are looking at also hurricane hazard. And we have another test bed that demonstrates how that works. The latest development is that our expansion to different types of assets. So we are not only looking at buildings, but we are also interested in lifelines, and hopefully we can add more types of assets in the future. And we have another test bed for Memphis, Tennessee, that demonstrates how that works. These test beds show regional analysis, but of course, all of these features are available for individual structures as well. So once again, please check out these resources. These are links in the presentation that you download, and let us know if you have requests for other types of features, or if you would like to see other types of developments in Pelican. And now let me show you how to run the loss assessment with Pelican, if you wish. So again, I'm going to make this a little bit smaller and show you this script. I think I've already pointed that out, but just want to make sure that you will be able to find it. So it's in your PBE folder, there's an applications. Within there, there's perform DL and Pelican. And this is the DL calculation script. I recommend you to start with that. And later, of course, you can include Pelican functions directly in your application if you are writing a Python script. But this is callable from MATLAB or from any other scripts. So it makes it very easy for you to run Pelican without the need to go through the user interface of PBE if that's what you desire. You will need two types of input data. You will need a configuration file and the response file to run the assessment. This configuration file you can obtain by saving the settings in the PBE JSON file, or even easier, just go to the template directory where you run the analysis. And here you have this Dakota JSON file, which is a configuration file for Pelican. So you can take that and run the analysis. Another option for today, you have the example zip file, and there is a 6-story BRBF _ Pelican, which I prepared specifically to run the analysis using the DL calculation script. So you can use that in your tests. The response CSV file is the same one that you would provide to PBE. So in this case, it's this file. It's also part of your zip example archive. When you have both files available, you might want to either rename this Pelican file or replace DL config with the name of the file. So pay attention to that. You can run the analysis with this command. So this is what you would need to run in a command line to run Pelican analysis. Make sure you replace these asterisks with the path to your DL calculation Py script. I cannot know where it is in your computer, so that's why I left it like that. The file name is the file name for the configuration file, and the EDP file is the one responsible for the response assessment. So all you need to do is pull up a command line. I believe I prepared one here. Yeah. And I should have, yeah. this command here, this is the same command that I just shown here. You see that it's Python, is the path to my DL calculation script, the DL file name, and the EDP file name. And then I execute this script in a folder where I have the files. This is also important. So before executing it, let me show you that I have a folder right here that I created for this purpose. I have these two files. Okay, and I run this command from that folder. So when I hit enter, I can see what is happening. I can see warning messages if something is, it's not really an error, it's some information that is good to know. For example, in this case, because we are truncating the distribution of EDPs, we only have a few samples left, and that small number of samples is not enough to estimate the correlation matrix properly. So the EDPs are going to be uncorrelated in this case. And then the analysis is running right now. You will be able to monitor what is happening here. I will continue with the presentation in the interest of time. So this is how you run the analysis. Now, a couple of pieces of information related to these analyses. You don't need all the details in the configuration file that is provided by the PBE application. So if I show you a configuration file, this is the one that is used by PBE. Again, as I shown at the beginning of the presentation, we have applications here, we have the damage and loss part, and then we have a couple of other things that are needed for structural response estimation, if that's what we want to do. Now, if we don't want to do that, if we are only running a loss assessment, we have this other file that I also included in your zip examples with the underscore Pelican, where I removed the unnecessary or the extra data. So we only have the damage and loss and the general information part. I wanted you to know this because you might want to generate these files from a MATLAB script. So there's no need to generate all of these parts. You only need to pay attention to these other settings that are related to loss assessment. And if you start reading this, you will see that this is exactly the same information that you specify in the PBE application. All right, so that's one thing. The damage and loss database that you want to use for these, the database that you might set here when you specify the damage and loss data folder is specified under the component data folder here. So if you want to use your own component definitions, your own fragility definitions, you want to update this folder to the location where you have those JSON files. You can export various databases. We have the default FEMA P58, but we also have others. If we go here to the PBE application, oh, it's in the other one. Yeah, so we have the PBE here. This is your zip file that you downloaded from DesignSafe. You go to Applications, Perform DL, Pelican, Pelican PBE, and then Resources. And these are the various databases that are available in Pelican. These are not exposed to PBE, only the second edition of FEMA and the HAZUS EQ one are available there. But we have the equivalent PGA database for HAZUS, and then there's another one where we use story-based assessment in HAZUS. This is a hurricane database for HAZUS, and this is the first edition of the FEMA P58 data. And here is the script that you can use to export these data to JSON files, just like you do it in the PBE application. So you can find that script here, just next to the DL calculation script. And here is how to use it. I'm not going to demonstrate it because we are a bit late, but I believe you can copy this script and just fill in the gaps here with the paths, and you will see that it exports the database into a list of JSON files. And finally, what I wanted to mention is that Pelican is used by the DL calculation, but it's just a script. So you can go beyond that. You can write your own script and include Pelican in there. And just again, to give you a quick look how that works, here we have an example with the DL calculation. So you can see that most of the work, the loss assessment, is done around like lines 250 if you open the file. So this is how it is calling Pelican and running the various steps of the assessment. Everything else, the 250 lines before that, are pre-processing steps and just making sure that it works well with the PBE application, or it makes it convenient for you to call it from a MATLAB script, for example. But if you have a Python code, you might want to include these lines directly there so that you save the time that it takes to do the file operations and saving files and loading files. This is interesting if you want to run a large number of buildings, for example, or a large number of assessments in the same parametric study, for example. But if you only want to run a single building, then there's not much speed increase or efficiency increase in moving away from this script. So if you only want to run individual buildings, I believe that the DL calculation Pi is a good way to go. And even the PBE tool is a good way to go because it just makes it much easier to set up the assessment than writing the file by hand. So that's how these things are layered on top of each other. The PBE tool is a user interface for basically the DL calculation.py as far as loss assessment goes. And it's also providing you much more features by having the whole workflow available. And then Pelican is really for those who want to run large scale assessments of multiple buildings and multiple types of settings. Okay, I would like to use a minute to also show you the roadmap for PBE and Pelican. But before we go there, I believe that the analysis here is done. So remember that we ran Pelican directly from the command line. You see that Pelican calculation is completed. And if we go back to that same folder, I'd like to show you that we have the results there. So it was in this demo folder. And you see that these CSV files were generated in that same folder. So wherever you run the analysis from, that's where you will get the results in the end. Okay, so last two slides, just to give you an idea of where we are going with this PBE and Pelican tools. First, we will have a major release at the end of 2020. That's roughly around October or November, I hope. PBE is always a step behind Pelican because we want to make sure that the features are vetted before they make it to the PBE tool. So for PBE, what we are expecting by the end of this year is that we will have wind events in there. We will be able to have the whole workflow for wind. So it's not only the loss assessment part, but you will be able to generate and simulate response of buildings to wind hazards and then get damage and losses from that. And I also plan to extend the user interface for you to be able to edit the fragility and consequence functions directly from PBE. When it comes to Pelican, it will go and include, it already has the wind-related damages, and now in this year we will include water-related damages and losses and the corresponding databases. We will extend the capabilities with the lifelines and make those databases available. And I'm also working on auto-population for performance models. I think it's an important topic, but we would like to make it very transparent and driven by files that people can share with each other so that there could be auto-population strategies developed by the community that we can share among ourselves. And finally, time-based assessments are an important step to include in Pelican so that you don't have to run separate sets of EDPs when you want to do such an assessment, but we will take care of aggregating such results. In the longer term, PBE will have these water hazards and time-based assessments from Pelican beyond 2020, also the auto-population, and we are looking at enhancing repair time estimation. I mentioned that yesterday already. I'm not sure what the deadline for that is, but it's a topic that we consider very important. In Pelican, beyond 2020, I'd like to include more databases beyond HAZUS and P58, thinking about other parts of the world where they might use different data, and response estimation without simulation. This is especially important for regional assessments. And we are looking into various methods to have in there. I have a list of exercises in the presentation as the last slide. Please take a look, and if you have a chance, try to do these exercises and join us for the office hours at 2 p.m. If you are experiencing any trouble, or if you would like to ask a couple of questions related to the exercises. And with that, I am done with the presentation. Thank you for listening. And I would like to hand it over to Grace. I'm not sure if she's controlling the recording.
Adam, thank you so much for this very informative presentation on behalf of the audience. And thank you for mentioning the fact that we do have office hours at 2 o'clock. I will stop the recording right now so we can close out this meeting.
Thank you.